So the max cut problem is to maximize 1/2 sum of 1 minus xi xj over all ij in E subject to xi square equal to 1 for I from 1 to n. This we agreed, right?
Yeah.
This is the problem. Okay, so then the trick was you take one of these characteristic vectors of cuts, like this plus minus 1 vector, and then we wrap it up, you make it into a PSD matrix. So let's call this XS. And this has the property that XS is PSD. It has the property that sorry, I keep writing S. Let's remove the S. It's okay, actually. I'll just remove the S from here. Okay, so X is PSD, and then XII is 1 for all I. So I'm just listing some properties. And the other property I have is that the rank of X is 1, right? Because it's the outer product of a vector with itself. Okay, so this is, and then you can check that if you have any X with these 3 properties, it exactly comes from inner producting a plus minus 1 vector with itself. Okay, so that you have to argue a little bit, but this set over here is exactly in bijection with this set over here, okay? Okay, so we've lifted from Rn into n by n PSD matrices, but there is this rank condition which is not convex. It is not a nice condition, okay? So typically, so the SDP relaxation is to drop this. So we drop the rank condition, and now we have a region that is basically the PSD cone. So the PSD cone, the cone of all PSD matrices is a convex cone. So we have that with a whole bunch of linear equations. So that means we are cutting the PSD cone with some affine plane. And the feasible region here is that's the feasible region. That's definitely convex because we're cutting a convex set with a convex set. That's a feasible region of that, okay? But now let me write the objective, which is the part that was not clear before. So that objective is the same thing as maximizing 1/2 sum ij in E. And then notice that this xi xj is exactly the ij entry of this matrix. Okay? So remember, so if I have x, this is the outer product. So if this is xi and this is xj, then in the ij entry you get xi xj, okay? So this is really 1 minus the ij entry of the matrix xij, subject to the condition that xii is 1 for all I and x is PSD. Okay, so this is a linear objective in the entries of this matrix. Okay, so this is completely, do you agree?
So then we think of this as polynomials in n choose 2 variables.
Yeah, if you want to make it polynomials. In the world of matrices, this is now completely okay. It's a linear objective in matrix space, subject to...
We are treating the variables as continuous variables.
Continuous variables.
But here, xi squared is...
So it's a relaxation.
Yeah.
It's a relaxation, right? So when you solve this, you may or may not get back a matrix that has rank 1. If it has rank 1, you know that it came from a plus minus 1 vector times itself, and then you get a cut, right? So typically what's happening is that, so rank 1 we don't know, but we're getting some region. What we may really want is this region. This may be the true region. Actually, it's not, it's a collection of finite, it's a discrete set, exactly. So you get some relaxation, you solve the objective, you get something. You get some matrix, which we call X star. If that has rank 1, we're good, we're done, right? But typically it doesn't have rank 1. And the big result of Gomez and Williamson from like 1994 is that whatever you get here, this X star, there is a very clever way to round this to a cut that is guaranteed to be at least 0.878 times the max cut. Okay, so if this is the max cut, then the cut that you get is greater equal the size of the cut that you get from this algorithm is at least 0.878 times the max cut. It's a very, very good result. And if you can improve, so this comes from what's called the first SDP relaxation. If you can improve that approximation constant by epsilon, you will break the unique games conjecture. Yeah, so it's a very big, it's considered probably unbeatable by this first SDP relaxation. It's not just the first, it's maybe a little bit more complicated statement, but it's a very important computer science result. Okay, so let's talk about, so there we have the definition of SDPs. So this is the first exercise. I'm going to leave it to you. Maybe we'll do it later. Yeah?
That kind of problem, it's half summation 1 minus xi xj. That is total number of edges between is and is, right?
No, it's over all edges because by that argument I just made before, you see if the edge goes from, if the edge is entirely inside one of the S or S bar, it doesn't contribute.
It's 0 then. Otherwise it is like whatever in between
Is 1.
that is coming out.
Correct.
But our motive was to minimize that number.
No, maximize. This is the max cut problem. Minimizing cuts is polynomial time solvable. Okay, that's an LP. It's a linear program. Maximizing cuts is NP hard. And the thing we did on the first day is sparsest cut. Yes. That's something else. Okay. That's more like minimizing, but it's not exactly, right? Because it was a ratio of things. Yeah, so this is called the max cut problem. It's one of the quintessential NP hard problems. Okay, so let's start talking about examples of SDP. Okay, so the first example I want to do is linear program. I want to argue that a linear program is a semi-definite program. Okay, so let's start there. So let's start with a linear program of the form minimize, I guess. Yeah, minimize C transpose X subject to AX. Is it okay if I write it like this? Everybody okay if that's still a linear program? Yeah, so if you want to put it in the other form, you just take the B to the other side. You have AX greater equal to, okay, maybe this is already too hard. Okay, let me write it like this. Okay, so this is a linear program. Everybody all right with this? So I want to argue that this program can be rewritten to look like this. Okay? So the C transpose X part is okay. We just have to rewrite this system as a linear matrix inequality. Okay? C transpose X is fine. All right, so how are we going to do that? So let's think about, so now let me do the transformation that I had just done before. So I can bring this B to the other side, right? As a minus B, that's all right. So let's do that. So let's write this as minus B greater equal to 0. I haven't really changed anything. And then can I also just make it plus? I have to change, it's not the same B, you have to use a different B, but I can assume the linear program comes to us like this. Okay? So let's just assume that. We could leave the minus if you want, but this is fine. Okay, so now let's think about what this is, right? So what this is so I'm going to write out the first inequality in this system. So the first inequality is A11 x1, A12 x2, plus up to A1n xn plus B1 greater equal to 0. Okay, that's the first inequality in this inequality system. And now I'm assuming there are n variables. Okay, it doesn't matter, but we could assume there are m variables. Why not? Let's do that. And then the last one is going to be some, I don't know, let's give this matrix a size. So maybe this matrix is like L by M or something. So this is L1 x1, AL2 x2, plus up to ALM xm plus BL greater equal to 0. Is that okay? I just wrote the system out in its full glory. So that's what that is.
So it's 1 by 1 matrices basically.
Yeah, so now I want to wrap this up to look like some matrix. So what are we trying to do, right? I wanted this to be some matrix times x1 plus some matrix times x2 plus all the way up to some matrix times xm plus a constant matrix. I want this to be PSD. This is what I really want, okay? So we need to convert that system to look like this, okay? So let's do the x1 first. So x1 comes with all of these, right? So do you see what we have to do? Make the first column the diagonal, right? So this will be A11, A21, all the way up to AL1. So that will pick up all the x1s. And then we pick up the x2s by doing the same thing. So this is A12, A22, up to AL2. So I pick up everything there. And then similarly A1M, all the way up to ALM. So this picks up all of those bits. And then here we just have to do the same thing. So we go B1 through BL. So this has picked up all of that stuff. Do you agree? So I'm still going to talk about the inequality in a bit. But the function part is exactly this, okay? So it seems kind of wasteful, but it's exactly this, okay? So then what we needed is that all of these things are non-negative. That's what we want. But you see, when you add this up, you have a diagonal matrix, right? When you add everything up, you still have a diagonal matrix. So diagonal matrix being PSD, if and only if all the diagonal entries are non-negative, right? Because all those minors have to be non-negative, so it shows one direction. So a diagonal matrix being non-negative implies it's PSD. But if you have a PSD diagonal matrix, I claim that's the same thing as the diagonal being non-negative, okay? So a diagonal matrix being non-negative is the same thing as the diagonal matrix being PSD. So this may be check, okay? So claim is that a diagonal matrix, let's call it diag of alpha 1 to alpha m. This is PSD if and only if alpha 1 through alpha m is greater or equal to 0, okay? So modeling the PSD-ness of a diagonal matrix is just the same thing as requiring the diagonal to be non-negative.
It also depends on the signs of x1, x2, x7.
They are variables. They're variables, right? So I'm just trying to model this system of inequalities as a linear matrix inequality. I don't know what they are. They're variables, right? So
Want x such that this is...
Exactly. We're looking for all the x1 through xm's that satisfy these conditions, which means it has to be inside a polyhedron. That's what it means to satisfy these conditions. But I'm saying that's the same thing as you can rewrite that system as a linear matrix inequality by doing this diagonal trick. Is that okay? Any questions? Okay. So then at the end of the day, what we have proven is that, so what is this, right? So this problem in the top, this becomes the same thing as minimize C transpose X subject to this whole LMI, okay? This whole thing at the bottom. So the whole thing at the bottom, we can call this matrix A1, we can call this matrix A2, all the way up to AM, and we can call this matrix A0.
That means our A, B, both are into as positive also, not non-negative.
Which AB?
That matrix A,
This is non-negative?
into is also non-negative.
No. I'm not requiring that this diagonal matrix is PSD. I'm requiring that when you sum this up, you get something that is PSD, right? So the x's have to work in a way that when you finish the sum and you evaluate at the x's, it's non-negative. This is definitely not necessarily non-negative. That would be very special, okay? So this is the same thing as this A0 plus sum of AI xi being PSD. Everybody okay? Okay, so this is the first example. So LPs are SDPs, okay, where you model PSDness using diagonal matrices. And then do you see that means also that polyhedra are spectrahedra, right? Spectrahedron means anything that looks like this, X such that this inequality system is true, okay? We just argued that polyhedron, which is anything that satisfies something like this, will also satisfy a linear matrix inequality, okay? So polyhedra, anything that satisfies these conditions, looks like this. These conditions are the same as writing this long PSD condition. Anything that satisfies a big PSD condition like that is called a spectrahedron, okay? So polyhedra are special cases of spectrahedra. So they are curvy, like we saw in the bubble thing, but these are also fine. These are spectrahedra, but they can also be curvy. They can also be curvy, okay? So there are more sets that are spectrahedra than there are polyhedra. Okay, good time for a question. This was example 1. Okay, so maybe if there are no questions, let's do another example where we move away from linear things, okay? So linear programming has linear objective, linear constraints, very, very special. They happen to be, you can model them as an SDP, that's fine. But let's actually now work on a problem where the objective is not linear. And so it's definitely not a linear program, but we will then argue it's actually a SDP, okay? So in this next example, what I want to do, example 3, what I want to do is I want to take a polyhedron. So this is some polyhedron P. It satisfies AX less or equal to B, okay? And I want to pick a point outside, like say little p, okay? Think of this as some model for some physical thing. This is an observation. The observation is usually noisy, so it doesn't actually fall inside the set of actual solutions. It's something outside, like if you're in a lab and you're measuring some, I don't know, distances between electrons in a molecule or whatever, atom. Then this is your observation. This is the actual set of possible solutions. So typically in experimental work or in applied work, you want to find, you know that this point doesn't satisfy the constraints, but you would like to find the closest point to the set of solutions that does satisfy the constraints, okay? So this is the basis of maximum likelihood estimation. For example, you have an observation, it doesn't quite fit the model. You have some equations that you know have to be true. It doesn't quite fit those equations, but you have an observation and you say, okay, I'll just go to the closest point that geometrically that satisfies all the equations, okay? So think of the polyhedron as the place that you should be in, but your observation is outside. So I'll be happy with this point. So let this point be X star, okay? So this will be some point X star, and that we're going to report as the correct answer, okay? It's not, because this is how the world works, right? It's always noisy. There's nothing exact outside of the math classroom. Mm-hmm. So when you do experiments, you have to be willing to do this optimization over and over again, okay? And the metric that you use for distance varies depending on the field that you're in. So I'm just going to do Euclidean distance today, okay? Just geometrically, what's the distance? What's the closest point to that polyhedron? Okay, from my observation. All right. It's like, yeah, it's an error, correct. So finding the closest point minimizes the error, right? It minimizes the gap, yeah. Polytopes are special cases of polyhedra. Polyhedra just means anything that satisfies AX less or equal to B.
If our P come to the, like there is open space can be there, like it may not be bounded.
Yeah.
So if P is suppose like up, like there
Okay, I think you're over worrying, Aditi, but let's try. So, okay, so it could be this, right? So if I have of course, if you're here, then you're already inside the polyhedron. The closest point to you is you, right? So if you're here, then this is the closest point. If you're here, then maybe this is the closest point. Got it? Okay, good question, but yeah, it's good to be worried. Okay, so let's actually model this, okay? So how do we model this? So what we want to do is to minimize the distance from P to X. Okay, this is what I want to do. Let's just square it, 2 norm square, so that I actually get a polynomial, because if you just take norm, you have a square root. We don't want that. So minimizing the square is the same as minimizing without the square. I just want to find the closest point, subject to the condition that AX is less equal to B. Everybody okay? This is this problem. I want to minimize the distance from my given point P to the polytope, in this case I drew a polytope, subject to the conditions of the polytope. Yeah? This is not a linear program. Do you agree with this? The constraint set is fine, it's a polyhedron, but the objective is a quadratic function. This is definitely not a linear program. Yeah? But I'm going to argue that this you can write as a semi-definite program. Therefore, we'll have algorithms to solve this. Okay? There are many algorithms to solve this even without semi-definite programming, but let's actually argue that it's a semi-definite program. Okay, so for this, so here's the trick. So what we're going to do is we're going to introduce a new variable called t. Okay? And I'm going to require that t is greater equal to x minus p norm square. Okay? So I'm going to introduce a new variable. I'm going to require that t is greater equal to this sum, and then I'm going to minimize t. Okay? So I'm going to minimize t subject to the condition that t has to be greater equal. So the best value of t is going to be the best value of the norm square, right? And I also have the conditions that ax is less or equal to b. This I need, right? I need x to be inside the polyhedron, but I now have one more variable, a new variable t, and I'm going to minimize t subject to t greater equal to x minus b norm square, ax less equal to b. All right? Maybe think about it for a second.
So in principle, it could be possible that the minimum value of t is attained not at the boundary, in the sense that t could be larger than.
Yeah. We are allowing a bigger feasible region, but the best value of t is going to be the exactly attained when x is the closest point, right? If x is not a close point, if x is like far away here, then this minus this norm square is t. But the best value of t, which is the minimum value t can take, is going to be achieved by exactly this x star. Okay? Now, x star may not be unique. Sometimes it's not unique. Like, for example, if your point was sitting here, I don't know, what's a good example? Yeah, so there are examples you can construct where it's more easy to see, it doesn't apply here, but if you had a set like this, and then you have a point here, then there could be like 2 places where the minimum is achieved, right? I think maybe in a polyhedron it won't. I don't know. Let's think about it. Yeah, maybe. Maybe, at least in my picture, yes. Okay, so this is good, okay? So what does this achieve for us? It made the objective linear. This is important, right? The objective was quadratic before, and if you want to write an SDP, we need the objective to be linear. So this already made the objective linear. It pushed all the non-linearity into the constraints, but that's okay because SDP can handle non-linearity. So it seems like we are going in the right direction, okay?
Because t is not present in any other constraint.
Yeah, t is a brand new variable, okay? It's not present anywhere. So I'm minimizing this t where t has to be greater or equal to this quadratic, and x only x has constraints on it. Make sense? Okay, excellent. Okay, so this we already know how to write as an LMI. That is what this is, right? This bottom bit we already just studied how to write as an LMI, so that's okay. So let's think about how to write this as a PSD condition. I want to turn that into a PSD condition, okay? So saying T greater equal to that, I want to say is the same thing as saying something is PSD. Okay, so for this we need a lemma. So I'll keep this at the bottom here. Actually, let's bring this over here, right? So this we already know is an LMI. So let me not even bother to write it, but it's whatever this is. So this stuff we can use to write that bit, right? Okay, so the lemma I need is something called the Shor complement. So I'll just write it down. I'm not going to prove it. The proof is on Wikipedia. If you're interested to look at it, you can also try it. So there's something called the Shor complement. Oh, yeah, it's in your exercises actually. So you can read it. So it says that if X is a symmetric, so this is called the Shor complement lemma. Okay, so this says is if X is a symmetric matrix and it's blocked like this, A, B, B transpose C, okay? So it's symmetric, but I can write it in block form like this, okay? So if that's the case, so we're given this, and the claim is that if the first block A is positive definite. Okay, positive definite means that the eigenvalues are strictly positive. Okay, so this is the inside of the PSD cone. So this means that, so the word is positive definite. So this means, okay, let's talk about this for a second. So this means that so this by definition means that all the eigenvalues are strictly positive. That's one definition. Or it means that, let's see what is the best one to use. All leading principal minors are positive. So leading principal minor means that you only take the 1 by 1, the 2 by 2, the 3 by 3. You just like walk like this from the top. You don't take all possible collections of rows and columns, but you just take, first column, first row, 1 and 2, 1 and 2, 1, 2, 3, 1, 2, 3, and just like walk down through the diagonal. Okay, there are only linearly many of those, right? Those are the leading principal minors. So they are positive. So in particular, the determinant is positive, which means the matrix can be inverted, okay? In general, PSD matrices cannot be inverted. They may lie on the boundary because if there's a zero eigenvalue, that means there's a kernel, cannot be inverted, okay? But these can be inverted. And the geometry of the whole thing is that the set of PSD matrices is a cone, and in the interior of this cone lives the positive definite matrices, okay? And in the boundary of this cone lives all the other PSD matrices. So in the boundary you have PSD, but in the interior you have positive definite. And that makes some sense, right? Like as the eigenvalues are a continuous function of the entries. So as you go towards the boundary, the eigenvalues can limit to 0, some of them. And then you won't be invertible, you'll be on the boundary. But in the interior of this cone, you will be a positive definite matrix, okay? So,
How we observe the cone, like it's quadratic equation you are saying, no?
sorry?
This cone is constructed from the quadratic equation, like X and
Yeah, you can construct this in many ways. One is to write or say that all the principal minors are non-negative for a symmetric matrix.
cone, I'm saying.
Yeah,
How you construct the cone?
exactly that way, right? So you can say different definitions. Sorry, Arvind, you were explaining? Yeah. So PSD cone has many descriptions. So the PSD cone, let's actually give it, so it's usually written like this, Sn plus, okay? So Sn is the space of symmetric n by n matrices. Sn plus is the set of PSD matrices. So this is the set of PSD matrices. And okay, so first of all, can you quickly think and see that it is a cone? If I take something PSD and I scale it positively, still PSD. Which definition is good for that? So A PSD, not positive semi-definite, just PSD. Okay, so eigenvalue is non-negative. What happens if you scale a matrix positively to the eigenvalues? It just scales, right? The eigenvalues scale. So if they are non-negative to begin with and your scaling is positive, still non-negative eigenvalues, right? So it's a cone. That's a cone. Okay. Next, you have to check it's a convex cone. It's not like some cone like this, where you cone over that. That's a cone, right? You can scale. You can scale things positively. It stays inside there, but it's not a convex cone. But it's a convex cone. So how do we check that? So if A and B are both PSD, can you check that if you make a combination, that's also PSD? So alpha is between 0 and 1 now. Which would be good? Which would be the right definition to check that it's convex? You can check non-negative eigenvalues. That's true because 1 minus alpha is non-negative. You could check that. You could.
But you cannot sum
No,
eigenvalues.
you cannot sum the
But
But leading principal value.
no, you should take X transpose A.
Yeah, you can check the quadratic form, right? So quadratic form will tell you that we already had X transpose AX is non-negative. We already have X transpose BX is non-negative. So now you just do this X transpose X and then argue that that's non-negative. Okay, so it's a cone, it's a convex cone. Okay, that's why I'm drawing the pictures like this. So the picture I'm drawing is like this. Okay, but it is living in the vector space of n by n symmetric matrices. So the ambient space is n by n symmetric matrices. Inside that, it is a cone that's convex. Okay, so it is like the positive orthant of Rn. Okay, so positive orthant of Rn is a cone, convex cone, inside Rn, right? And similarly, this is a convex cone inside Sn, the space of n by n symmetric matrices. So you should think of this as the positive orthant of the space of n by n symmetric matrices. That's one way to think about the PSD cone. Okay, and
It's not a polyhedral cone.
it's not a polyhedral cone. So how do we describe it? That's what Aditi was asking. So let's try to explain that. So how can I describe it? If I want so this is the set of all x's in Sn such that x is PSD. This is what it is by definition. But x being PSD is saying that all the principal minors are non-negative, right? So every principal minor is a polynomial in the xij's. Right? Every principal minor is a determinant with using sum of the entries of x. So x is an unknown variable, unknown matrix. It's filled with xij's. So when I make principal minors and say it's non-negative, I get a lot of polynomial inequalities. Yeah? Okay, you want an example? Yeah, we saw that before exactly, but this here we don't, there are no scalars or anything, right? We're just saying x11, let's do it for 2 by 2. This is the same because it's symmetric. So 2 by 2 PSD looks like A, B, B, C. This is a symmetric 2 by 2 matrix. If I say this is PSD, that's the same thing as saying A is non-negative, C is non-negative, and AC is greater equal to B square. Okay, so that's the description of the PSD cone. And one nice thing is that this boundary is actually cut out by the determinant. Okay, now the determinant, I don't know if you've seen a picture of the determinant equation. So the determinant, if you draw the equation AC equal to B square, you draw the whole space. It'll have lots of things. It'll have some places where A and C are negative. It'll have some places where A and C are positive. It'll have all kinds of things. So you do need these other things to actually fully cut out the cone. But the polynomial that vanishes on the boundary is exactly this, okay? I'll show you a picture later, please remind me. So if you just take the determinant, it's sort of a wild thing, but you need this extra pieces to cut it out, okay? So it's a convex cone cut out by these polynomial inequalities, okay? So it's a semi-algebraic set. Semi-algebraic means you're cut out by polynomial inequalities. Algebraic means you're cut out by polynomial equations. That's algebraic geometry. If you have semi-algebraic things, you're in the world of something called real algebraic geometry, which is a cousin of algebraic geometry. Okay, good. And then the key piece is that in the interior of this cone lives the matrices that are positive definite. So this is the notation for positive definite, which means all the eigenvalues are positive. Okay? So maybe you can think about that later. So how do you show something is in the interior of anything? Yeah, you have to show there's a ball around it where it's all PD, right? Do you see why that is the case? If I have a matrix whose eigenvalues are positive, and you wiggle the matrix entry slightly, what happens to the eigenvalues? Still remain positive, right? You can make a small enough ball because eigenvalues are a continuous function of the entries. So if you take a matrix whose eigenvalues are positive and put a little ball around it, you're just like wiggling the entries of the matrix. So if you make slight perturbations, the eigenvalues will perturb slightly. But because they're all positive, you can perturb, there will always be a small ball where the eigenvalues will stay positive. That's the reason. Okay? So the interior consists of positive definite matrices. The boundary consists of everything else. Yeah?
For this argument to begin with, we should have at least one positive definite only.
Yeah, what's an example? Good question, Anissa. What's a classic n by n positive definite matrix? Identity, exactly. So identity definitely sits inside, right? So, and if you wiggle the identity, which means you just perturb the diagonal, maybe you put some little entry somewhere else, it'll continue to have positive eigenvalues, right? The eigenvalues are 1, 1, 1, 1, 1. There's no way it'll just boom go to 0 if you make a little wiggle, right? So it has an interior, good. And the interior is exactly all these positive definite matrices.
One thing that we shown that Sn plus is connected by convexity. Right?
By convexity. It's a convex set. Okay, so it's definitely fine. Okay, I think we know a lot about this cone now, right? In higher dimensions, it doesn't look like this. 2 by 2 does look like this, but as soon as you go to higher dimension, it's a pretty complicated cone. It's not so simple to describe the PSD cone, okay? But it's still nice enough. Okay, so then let's come back to Shor complement. So it's saying that if this matrix is positive definite, then we can do something. Then, then X is PSD, the big matrix X is PSD, if and only if some other thing is PSD. So X is PSD, if and only if C minus, B transpose A inverse. So remember, I can invert A because it's a positive definite matrix times B is PSD. Okay, this is a very useful trick. And so it's saying, so basically what we're doing is we are going C, you're starting in this corner, and you're doing C minus B transpose AB. So you're kind of moving in the circle from C around, and you're saying B transpose A inverse B has to be PSD. Okay?
And A inverse exists because A is positive.
Exactly. A inverse exists because A was positive definite. Everybody all right? So, and there's a symmetric version where you can say that if C is positive definite, then A minus B, C, whatever, B, C inverse, B transpose is, okay, that's a symmetric version, okay? Good, this is called the Shor complement lemma. So now, back here, let's use it to model this as an LMI. Okay? So can you see that this is really this kind of thing for a particular way, particular blocking of stuff? Okay? So I want to show that this minus this works, right? So let's rewrite this. So this is the same as T minus X minus P transpose X minus P. Do you agree? Norm square is X minus P transpose X minus P.
So I think maybe one thing to clarify is that B may not be a square matrix in the Schur complement lemma.
Oh yeah.
It could be rectangular.
Exactly. So the shape of this may be whatever, right? So it could be A is like this, B is like this, B transpose is like this, and C is like this, right? So we're not requiring anything to be of the same size. In fact, B and B transpose are not usually square, but C and A will be. Okay? Okay, very good. All right, so I gave you, this is my hint, okay? So we're trying to, so this being, this greater equal to that is the same thing as showing this T minus X minus P transpose X minus P is not negative. Everybody okay with that? Okay, excellent. Can we make it Schur complement of something? What is it? Yeah, let's make the block. So I want to make a bigger matrix where probably these two play the role of B, right? And there's nothing in it. What should we stick in the middle? Identity, right? Identity is a good one to stick in the middle. So what altogether should we have? Yeah, exactly. We could put, okay, I'll just do it this way. It's the same as what you're saying, Lavanya. So I'm putting the identity of size n by n here. T is 1 by 1. It's just a single variable. And then here we should put, if this is n by n, this better be x minus p, right? Because that's an n by n thing. And this better be x minus p transpose.
That's a column vector. Oh no, that's a row vector.
Yeah. Is that okay? So this is the blocking. So this is this is just one row and this is n rows. Yeah? Does it work?
You should take x minus p transpose.
X minus. So I should get here.
There you should take x minus p transpose and you below I is x minus p.
No.
But when you multiply, you take b transpose a b, right?
So this is C. So C is like our T.
No, that is already B transpose. X
Yeah.
minus P transpose is already B transpose.
Yeah. So remember this. So this is like our B transpose. This is like our B, and that is like our A, and this is like our C. Works out? So basically, requiring this condition here is the same thing as saying that this matrix is PSD by Schur complement. Yeah? Everybody okay? So that's the end. So then at the end of the day, what we have is we are minimizing T subject to the condition that I, X minus P transpose times, what is it, T is PSD. And then we had that other LMI, right, which is A0, which is the diagonal, or all these diagonals, diagonal of AI transpose X plus BI, A1, B1, this diagonal thing, AM transpose X plus BM is PSD. This was the big LMI that we constructed before, okay? So we have some, okay, so now I have two things that are PSD. This matrix is PSD, this matrix is PSD. How do we combine it into a single massive LMI? Just block them, exactly. So if I call this matrix something, let's call this matrix, I don't know, R, and let's call this matrix S, okay? Then requiring that R and S are PSD is the same thing as putting R here and S here in a block and requiring that this is PSD. Questions? All good? Okay. So this is an LMI. So that problem of minimizing distance to a polyhedron is exactly a semi-definite program. Okay? So instead of polyhedron, it could have been other things, right? You could have put other things like the sphere and so on. There could be other things that you can also express with an LMI that would work, right? So how would you, okay, this is a nice exercise. 12:30, okay. How do we express a disk as an LMI? Can you express x squared plus y squared less or equal to 1? Just the two-dimensional disk. Is this last part okay? Everybody got this? So if R and S are PSD, then this whole thing is PSD. You can check that, right? You can block it like this and collect it together. If you have software solving these things, you don't want to block it. You just give it the little PSD conditions. It prefers that. So it doesn't have a huge matrix to store, right? It has a bunch of little matrices to store. It understands that you got to block it. Everybody okay? Okay, so question for everyone. So I'm going to erase this short complement. It's in your notes, in your exercises, so you have the statement. So question, if you take the set x1, x2, or xy, such that x squared plus y squared less or equal to 1, we like this set. This is a disk. I claim this is a spectrahedron. Can we write it? That means you need to write it as an LMI, right? You can write it as something like this, greater equal to 0. Can you write, so can you express it with PSD conditions? So we want to turn that quadratic inequality into a PSD condition. I might not remember either, but let's try. Maybe. So when you write an LMI, you can only put linear things here. You only need a 2 by 2, that much I remember. You can only put linear things in those places, right? And then this has to be PSD. So it's some like short complement like thing you can do, right? And when you finish all the calculations, it should come out to be that. Okay. Yeah. Wait, what? Yes.
What's the 3 by 2? You want to use short complement.
Like this?
No. XY
Uh-huh.
and XY transpose. No, identity is correct.
Yeah.
XY transpose and 1.
Okay. This will work? So this is 2 by 2. 2 by 2. Okay. So now this is a 3 by 3 matrix. Yeah, it works, I think. Right?
Which way is the inequality? So 1 minus.
So we should have 1 minus xy, right? Is greater equal to 0. It's okay. Okay, homework. You can do it with a 2 by 2. Okay, so you need to be a little bit more clever how you make the quadratic. So there's so I'll leave that to you. So disks, ellipses, all these things are spectrahedra.
So does that mean that there can be multiple?
Yeah, there can be multiple representations of the same set, correct.
And then finding the minimal such is of what?
Yeah, so how in all optimization problems, how you model the set is really crucial. So different models are good for different things, okay? It's not unique. You may have different ways to model the same thing. Yes, this is true. Sorry, you have a question? Okay. All right, so I don't immediately remember how you write this with 2 by 2, but you can think about it. I think you need like an x minus y and an x plus y and all that. X plus y, x minus y, something like this. So, and then you do the multiplication, things cancel out, and it'll work out. Okay, so think about that. All right, so we are done with example 3. All right, we have enough time to do one more example before lunch. So we're back to graphs, okay? So let's do an example back to what we were talking about with graphs. And I want to show you that there are some natural problems on graphs that are actually SDPs. Okay. All right. So example 4. So I go back to a graph. Let's go back to a graph that has vertex at 1 through n, edge at e. But now I want to put weights on the graphs. Okay, so today I want to put weights, and tomorrow we'll also put weights on the graphs. So with edge weights, so the weights are on the edges. So the edge weights, let's call them wij, and they are non-negative weights. Okay, so this is true for every ij in E. It could be some of the weights are 0. Do you have a question, Abe? No? Okay. All right, good. So I'm allowed to put weights on the edges. So, again, example. Let's have a small example. So let's say this is vertex 1. Vertex 1 connected to vertex 2, connected to vertex 3, connected to vertex 4, like this, okay? It's still undirected, but I'm allowed to put weights. So I'm going to put weight 1 here, I'm going to put weight 2 here, I'm going to put weight 30 here, and no weight there, okay? This is all right, right? I'm allowed non-negative weights. One edge doesn't have any weight, that means it has 0 weight, but the edge is still there, okay? In some, I guess one way to, if you put 0 weight, you could also think of it as the edge doesn't play any role. But for now, I'm just weighting it like this, okay? Now, for these kinds of graphs, you still have a Laplacian. There's a weighted Laplacian, okay? And how will it be defined? So maybe you can just guess how it will be defined. Let's call it LW, okay? So this LW should have in position ij. So if you have an edge, then it should take the, what do you think? Yeah, you should take the negative of the weights. Before we were putting -1, right? Everywhere we had an edge, we put a -1 because it was like the weights were all 1. So now we put minus of the weights if ij is an edge, and you put 0 if ij is not an edge. So this is the case where I is not j. And then on the diagonal, what do you think we should put? Exactly. So we put the sum of the weights of all the j's that are adjacent to the I. Okay? Now that is plus. You add the weights of everything that is adjacent to I. Okay, so let's construct the Laplacian for this example. So this example has 4 vertices. So I have 1, 2, 3, 4. And I also have 1, 2, 3, 4. And let's do, for example, row 1, right? So 1 is connected only to 2. So here I should put -1 because that's the weight, right? Nothing here, nothing here. And then here I have to put the +1, right? That's the sum of the weights of everything connected to 1. Yeah? Sum of the weights. Okay. Let's do the rest. So what comes in this position? Sum of the weights of everything connected to 2. This should be 3. And then it's distributed as a -1 on the 1. And that's connected to... Sorry? Sorry?
Between 2 and 3, like that is.
Yeah, 2 and 3 is 0. Correct. Yeah. That's right. So it's a symmetric matrix, so I can fill this, and then I can also fill this. And then let's do 3. 3 has weight, total weight is 30. Yeah, -30, which means this is also -30. and then this must be 32. Okay, this is the weighted Laplacian. Okay, weighted, does it still have all ones as an eigenvector? Yeah, because the row sums are 0. So, and then that eigenvector has eigenvalue 0, right? So this always still has 0, 1. So 0 and the all ones is definitely an eigenpair. And it doesn't matter whether the graph is regular or anything like that anymore, right? I mean, even for the original Laplacian, we did not need regularity for this to work. Okay? And then you can also argue that this is PSD, just like the Laplacian. What might be the proof?
We are putting positive weights, so diagonals are positive and
Diagonals are positive, off diagonals are negative or 0. So before we use this BB transpose trick, right, to show that it's PSD, do you think you can use the same trick? Arbitrarily direct the graph, make the node edge matrix, put weights on it now instead of like 1 and minus 1. And then, yeah, so check that, it is PSD, okay? So let me not prove it, but this matrix is PSD. Okay, and it has this as an eigenpair, so it must be that 0 is the smallest eigenvalue, right? If it's PSD and 0 is already an eigenvalue, then it better be the smallest eigenvalue. So its eigenvalues still look like 0 is equal to lambda 1, is less or equal to lambda 2, all the way up to lambda n. This is how the eigenvalues still look. And it's still a symmetric matrix, so it still has a nice orthonormal collection of eigenvectors, okay? So the eigenvectors to go with everything. And you still have connectivity if lambda 2 is positive. Okay, so all of those results we saw before still hold. Okay, so if lambda 2 is positive, that's connectivity. This is an orthonormal eigenbasis. So nice properties still hold. Okay, so all that's great. So now I want to, so my graphs are connected, okay? So I'm going to make this a strict less than, because I'm only interested in connected graphs. So it's strictly less, okay? So now I want to come back to this problem that I mentioned a couple days ago. So you may have a graph system like underground electrical network, under the city.
one question.
Yeah.
Sorry to interrupt. We are considering where there is no weight, it's 0.
Yeah.
In general, we are considering always it is 1. Like
Yeah.
normal
In general, it's 1.
So if we put like 2 and 3, there is 1 edge. But we are considering 2 3 position as 0.
Yeah.
So if graph is connected, that
Yeah.
will affect the connectivity. The lambda 2 might become 0.
Yeah, you're right. So you could think of, if I put 0, you could think of this edge not existing. Okay? So that's really what you should think of. It's true. So it's true, you're right, that if I just start with some graph and then allow 0 weight somewhere, I'm essentially erasing the edge. So when you go back, you only get the graph without that edge. That's correct. Okay? So wait, so it's, yeah, so it's,
You can also make a connected graph into a disconnected graph.
yeah, if you put edges in the zeros in the wrong places, yes, you can disconnect a graph that way. That's also true. Okay?
Considering 0, so lambda 2 sometimes it can become 0. That is my point. Like, graph is connected.
Yeah, okay. I think I'm saying two different things. So in this particular example, okay, so I'm just saying that if you want your graph to be connected, lambda 2 has to be positive. Okay? Even if it's weighted, it has to be positive, and it's if and only if. Okay? Now, if you arbitrarily change the weights, lambda 2 may become 0, and the graph may disconnect. But the only claim I'm making is G is connected if and only if lambda 2 is positive. Okay? So in our example, we didn't disconnect. We're good. Do you have another question?
I was saying that in the age 1, 2,
Yeah.
like earlier, if we put 0,
Yeah, then you would disconnect.
then we will definitely get
Yeah, and then you can type it into your Mathematica notebook and check that lambda 2 becomes 0. Okay, so homework for the break. Yeah? Is there a question?
So someone was asking if you can prove that lambda 2 is 0 using random walks.
Lambda 2 0 using random walks.
Then the random walk will not be reducible. So you have multiple.
Yeah, perhaps. Yeah, I don't know exactly. It's possible you can do lambda, I mean, yeah. So then the mixing time will be, it'll never converge to uniform, right? If you start in one component, it'll never reach the other component. So mixing time will never reach to convergence. So then lambda 2 is probably something. Yeah. Yeah, exactly. So yeah, maybe. Yes. So good questions. Okay, so let's continue. So what I want to do is I have some fixed graph that I give you. Maybe to remove all the confusions, let's put a weight on this. So we'll put a tiny weight on this, 1/10. Okay. So wherever there were zeros, 2, 3, I will get 1/10 with a minus sign. Okay, then everything will change. Okay, all right. So I think I was just trying to give you an example, that's all, okay? This is not, let's put it back to 0. Okay, so what I want to do is I have a fixed graph structure. I'm allowed to change weights on the edges. So for example, you may be allowed to change the resistance of the wires that are connected in your graph, or you might be able to change the capacity, like you may be, if it's a road system, you may be allowed to increase the toll on certain roads or decrease the toll on certain roads. You don't want to like reconstruct roads. You already have existing roads, but you can mess with the amount of money you charge to drive on that road, or you can like do something else, right? You can have a lot more trucks going from one node to another node than you currently have. So you can change the weight on an edge, okay? So I want to know what is the maximum you can make lambda 2 by changing weights, okay? Now, if you make lambda 2 very big, then it means that you have all kinds of good stuff, right? You have like good expansion, information is going to spread through your graph very fast because the graph is more and more, it behaves like it's more and more connected, right? So a lot of people want to know this. So there are these papers by, Percy Diaconis and other people who've studied how to maximize lambda 2 by changing weights on a fixed graph, okay? So the graph is given, you're allowed to change weights, they have to be non-negative, and you want to increase lambda 2. So you will never go in the direction of disconnecting, right? Because that's making lambda 2 smaller. Yeah.
We just keep increasing the weight.
Yes. So good. So I do want to normalize the weights. Okay. So if you simply increase the weights, then that's scaling this thing positively, more and more positively. Lambda 2 will definitely go to infinity. Okay. So we do want to normalize the weights. So I want to say I want to maximize lambda 2, but it's a function of my weights. So let's write it as lambda 2w, subject to what we want to prevent, what Arun just pointed out. So I'm going to insist that the sum of the weights is exactly some number. Let's say it's the number of edges. Okay? So in the beginning, the weights were all 1, right? So the sum of the weights in that case is the number of edges. I'm going to just normalize it somewhere. You could make this 1, you could make it your favorite number, but fix it. Okay? So we're going to normalize the weights. So this is over all ij and e. And I want wij to be non-negative. This is the problem. Okay? Maximize lambda 2 after you have normalized the weights. If you simply allow weights to be whatever, lambda 2 will just go up. Why we normalize the weights? Oh, it's the cardinality of the edge set. Yeah, E is the edge set. So I'm just saying take the cardinality of the edge set, which is the number of edges. That's all that is.
That is how we will normalize the
Yeah, I'm just choosing to normalize like that. You could set it to 1 if you want, okay? But let me just normalize it like this, because normally when you have no weights on the graph, the sum of the weights is the number of edges, right? Because you have 1, 1, 1 on all the edges. So sum is what is that? So let's just take that to be our normalizing. Okay, is everybody okay with the question? Okay, that's right. So we got this. Okay, So now I'm going to make an argument that you have to pay a lot of attention to for like 1 second, okay? I'm going to change the, I'm going to show you that this is an SDP. That's where we're going, okay? This is an SDP, all right? Why? Okay, so first of all, I claim, okay, this is the part you should listen, okay? So what I'm doing is I'm fixing the sum of the weights and I'm maximizing lambda 2, okay? Weights are fixed, maximizing lambda 2. Only thing weights can do is move around, but it still needs to sum to E, okay? Maximizing lambda 2. I claim that's the same thing as fixing lambda 2 and minimizing the sum of the weights. Like we're trying to increase the gap between the two, okay? So if I fix the sum of weights to some constant and I want to push lambda 2 up, that's the same thing as saying lambda 2 is 1, what's the smallest I can push the weights down? Okay, this is the tricky part. So let me write it and then you can think about why it's true. Remember in optimization, we are happy with, so we want to, everything is up to scale, okay? So let me write it. I know this is going to be confusing, but let me write it. So I claim this problem is exactly equivalent. It's not equal, but it's equivalent to saying that I want to minimize the sum of the weights. It's not a dual problem. It's exactly equivalent to minimizing the sum of the weights, subject to setting lambda 2 to 1 and weights non-negative. Okay? Now, you see the two problems are related. Let's see, where is that? Sum of the weights. Okay, so there is like a cross, what do you call it? Like cross product? I don't know. So here the sum of the weights is E. Here the sum of the weights will come out to be whatever, something else, okay? Here lambda 2 is 1. Here lambda 2 is whatever, okay? So there's like a cross ratio type of thing that you can do, right? So in this problem, lambda 2 is whatever. The sum of the weights is this, okay? In this problem, sum of the weights is whatever, and lambda 2 is 1, okay? So the optimal solution and optimal value have to be scaled accordingly. So if I want, you have to do this cross product like we do in high school, and you have to say, if my sum of the weights is E, this is lambda 2. If I set lambda 2 to 1, what is the sum of weights? So whatever this is some answer. So let's call this W star. This is a number actually, right? This is a number. So what shall we call it? Alpha star, maybe. Yeah, W star. W star is not a vector, it's just a number. So they are related like this, the optimal value of the two problems. So W star is going to be equal to, W star times lambda 2 is equal to E. So I will get, yeah, it's going to be E divided by lambda 2. So they're not the same problem, but they're equivalent problems. I've just done a scaling trick to it, okay? All right, so that's equivalent. Okay, let's finish and then we'll come back and answer more questions. Okay, excellent. Now, let's think about this one more time, okay? So what are we doing? Now we are fixing lambda 2 to 1 and I'm minimizing the sum of the weights, okay? That's also a normalization, right? I'm fixing lambda 2 to 1, I'm minimizing the sum of the weights. And will it happen that when the weights are minimized, lambda 2 will be bigger than 1? Okay, rather, let me say the following. Will it be okay if I change this problem to look like this? Okay, instead of equal to 1, I write this, okay? What have I done? I have increased the size of my feasible region, right? I'm saying lambda 2 can be greater or equal to 1 instead of equal to 1, and I'm minimizing weights, okay? Now, if I minimize weights, the optimal solution is going to be when lambda 2 is 1, right? Because we are making the gap as big as possible. So there's no way that the optimal solution will choose something where lambda 2 is bigger than 1, okay? So even though I've increased my region, so for example, I can say, okay, my region of optimization is this, okay? And let's say I'm minimizing y, So I'm trying to go down, okay? Now, minimizing on this is the same thing as minimizing on just this. Do you agree? If I say, so the blue set is y equal to 0, and I can minimize y on y equal to 0, it'll be here, okay? But if I expand the feasible region to this, it's kind of useless. I'll still minimize on the original place, right? So that's the trick here. We're allowing lambda 2 to be bigger formally, but it's never going to be the value. In the optimal solution, I'm always going to get lambda 2 equal to 1 because we're trying to increase the distance. So if you're minimizing the weights, and lambda 2 used to be fixed at 1, but I'm now saying, okay, lambda 2 can be whatever, above 1. But if I want to make the gap as much as possible, this one is going to go to the lowest possible place, okay? So increasing the feasible region doesn't change the objective function and its value, okay? So I can do this. All right, so, okay, all of these steps are a little tricky, okay? But we have this. This is the final, next to final step. Now I claim that this is a SDP, this thing, okay? So we have to do a little linear algebra, right? So the only thing, this is fine. This is a linear function. We like it. This is somehow an LMI, okay? And this is also fine. This is just a non-negativity. We know how to model that, right? Put it on the diagonal of a matrix, make it PSD. That's okay, all right? So let's model this. I want lambda 2 to be bigger than 1, okay? So let me just show you how the trick goes. So let's start with the eigenvalues of the identity. Everybody okay? Eigenvalues of the all ones matrix. This is J. What is that? Yeah, so this one will be 1. N, yeah. So let me do 1 over n. So I have 1 and zeros. Okay? And then what happens if you do I minus 1 over nj? 0, 1, 1, 1, 1, 1. Okay, this is the smallest and these are the biggest. Okay? Okay, you can check that those are the eigenvalues. Okay? So the eigenvalues of I minus 1 over nj is all that. Okay? So if I have a matrix, any matrix, let's call it X, and okay, so there's a little bit I have to do. So I want to make sure that lambda 2, which is the second eigenvalue of the Laplacian, is at least 1. Okay? So if I compare to the Laplacian, I know that the first eigenvalue of the Laplacian is 0, so that I can't mess with. But after that, I have lambda 2, and I want this to be greater than this one. Okay? But then everything that comes after lambda 2 is even bigger than lambda 2, right? This is how this is going to go. So if lambda 2 is greater or equal to 1, these are all 1s. So I'm just going to get that all of these are greater than the corresponding lambdas. Do you agree with me? Okay. I'm trying to make lambda 2 greater or equal to 1. Okay. So if I can, if lambda 2 is greater or equal to 1, then lambda 3 is even bigger than lambda 2. So lambda 3 is also bigger than 1. So it's bigger than the corresponding eigenvalue here. So these eigenvalues are all 1 by 1 greater or equal to the eigenvalues of this guy. Okay? So now let me write a claim for you. So if I have two matrices, we're almost there. So if I know that A minus B is PSD, okay, A and B are two symmetric matrices. They may not be PSD themselves, but the difference is PSD. Then what can you say about the ith eigenvalue of A compared to the ith eigenvalue of B? Let's check. Is it true that this is true? 1 by 1, the eigenvalues are greater than the other one. Okay, let's argue this is true. What's the proof? So this is a question. Okay, this is true. All right. So this is true means we know X transpose A minus BX is non-negative for all X. Do you agree? I'm saying I'm given this. I want to argue this. Okay? I'm given that A minus B is PSD. I want to argue that means that 1 by 1, the eigenvalues of A are greater or equal to the eigenvalues of B. I'm going to prove that to you right now. Okay? That's a question. So I'm starting here, which means this. Everybody okay with this? Let's unravel this. So this means X transpose AX is greater or equal to X transpose BX for all X. Question? Somewhere? Good? Do you have a question? No. Okay. A minus B PSD implies this, right? This is definition of PSD, quadratic form non-negative, which is the same as this. Okay, now you can help me. Yeah. So this looks like something we know, right? How is this thing related to eigenvalues? In day one, we did something, right? With the quadratic form, I told you that lambda k is something. Yeah, Rayleigh quotient, Courant-Fisher, all that, right? So let's divide by X transpose X on both sides. This is still true. Okay? And now, can I put a min here and say that's greater or equal to min there? What do you think? Yes? It's like a weak yes. Is it a strong yes or a weak yes? I want to put min here and say it's greater or equal to min there. Yeah? This quantity for all x is greater or equal to the corresponding quantity for those x's, right? Whatever x I plug in, this is bigger than that. So the smallest this can be is going to be greater or equal to the smallest this can be, right? So this tells you that min of X transpose AX over X transpose X is greater or equal to min of X transpose BX over X transpose X. This is over all X. They have to be non-zero. Okay? So this is for all X. So then from this can we argue that the max of the min of X in S has dimension whatever is of X transpose AX over X transpose X is greater or equal to max min of the same thing. What do you think? I forget the exact thing you have to put there. But the min is greater or equal to min. So if I take max on this side, it's even bigger. This has to be greater or equal to the max of this. Okay? But this is exactly an eigenvalue. This is the kth eigenvalue, right? If this is dimension, I always forget if it's max or min. Yeah, it's some eigenvalue. Let's call it lambda question mark of the A matrix. And this is the lambda question mark of the B matrix. Okay? So what I get is that if I have this condition, then 1 by 1, the eigenvalues of 1 dominate the other one. Okay? All right, we're at the end. How do we write this? If I know this. Do you see what should happen? What are we looking for? We're looking for the eigenvalues of LW to 1 by 1 be bigger than the eigenvalues of this, right? That's the same thing. So saying that lambda 2 is greater or equal to 1, I claim is exactly the same thing as saying that the Laplacian is in this order greater or equal to or Laplacian minus I minus 1 over nj is PSD.
Can we use vector theorem for this? Like A and B both are PSD.
They're not PSD.
Sorry, symmetric.
Yeah.
Symmetric. So it can be written as U, B, U transpose. B cannot have same.
I mean, we don't know that they share the same.
Yeah, we don't know anything like that. But let's just finish arguing this. So hopefully you bought my argument there, right? That the eigenvalues are 1 by 1 greater. So I claim that if I want lambda 2 to be greater or equal to 1, it's enough to write this. Because this is forcing you to make sure that, okay, they both have 0 eigenvalue to start with. There's no problem. This has lambda 2. It'll be greater or equal to the second eigenvalue here, which is 1. That's what we want, okay? But then nothing else will get messed up because this will have bigger and bigger eigenvalues, like lambda 3 is bigger, but this one stays at 1. The eigenvalue is still 1. These are all 1. So nothing is getting messed up. So this can be modeled by writing this. Okay? So now that's the end. So we have minimize sum of the weights, which is okay, subject to the condition. So the way we write this is LW is greater equal to I minus 1 over Nj, right? So this A minus B non-negative, the way people write this is A greater equal to B, okay? That means A minus B greater equal to 0. So I get this, and then I have W non-negative. W non-negative. Okay. So maximizing the second eigenvalue is exactly this STP. This is an STP. Do you agree with that? This is a linear matrix inequality. If you want, you can bring it all to one side. This is non-negativity. That's fine. It's a polyhedron. That's also expressible with the LMI. We have a linear objective. So that's what it is. Okay. So in the afternoon, we'll talk a little bit more about this. You will see that this problem can be interpreted in terms of spectral embeddings and all kinds of stuff. Okay. So it's a very cool problem. It's been studied a lot, but I'm going to make a slight twist to it in the afternoon. Yeah.
This lambda 2, you take this one. This is something special about one. You can take anything equal to this lambda 2 equal to anything, or it is only one.
Oh no, I just normalized it to 1. You could set it to something else, but then you'd have to change the I minus 1 over Nj to something else, right? So I could have said I want lambda 2 to be at least 3. That's okay, but then you can't use this. Right here, I'm really relying on the fact that the second eigenvalue of this matrix is 1. Therefore, I can just write this matrix is bigger than that matrix in this lower order, and that'll force. Yeah, it's just a normalization. So a lot of normalizations happened here. So you have to be very careful to make sure you didn't make a mistake. Okay, good place to stop. And in the afternoon, I'll come back. I'll